Okay, looking around the room, it looks like about 75% of the class decided to take an early spring break, but thank you for those of you that are here, and if you can't make it, obviously, please, hopefully you'll follow through on the recorded video. That said, I want to remind you about the way the homework assignments are set up for the next couple of weeks. So if you're already in spring break mode, but you haven't done the homework assignment yet, you need to snap out of that for a bit, because we do have the Chapter 5 homework B is going to be due Sunday of this week, so in 3 days from now. And then the next homework will open up right after that, but won't be due until the week after spring break. So it's the Chapter 6 assignment that you'll have 2 weeks to do. If you want to do it during spring break, you can, but you don't have to do it until the week after. And there is a little bit of Chapter 6 material that we're not going to be able to cover until after spring break. So if you did wait, that's not the end of the world. It's just the stoichiometry stuff, which you could probably sort of figure out, but we are going to cover it after spring break. So today we're just going to do one remaining topic, and then we'll pick up with where we left off afterwards. All right, so the topic for today is redox reactions, and there is more or less an entire lecture devoted to it. And that's not necessarily because it's difficult, it's just different. It's something you haven't really seen before. It requires us to learn some new things, but once you sort of pick it up, I don't think it's too bad. So let's get into it. Before we get into the new stuff, though, let's just review a couple of things we did last time. So last time we talked about the first two major categories of aqueous reactions. So this chapter deals with aqueous reactions, and there's 3 types that are covered in sufficient detail to sort of classify them and learn some things about them. And the first one was called a precipitation reaction. And this is sort of when you have 2 soluble ionic compounds mixed together and one or more of the products, usually just one of the products, but sometimes both, are insoluble. So you swap the cations and the anions with each other. So let's do an example of that. Write a balanced equation for the reaction of sodium phosphate and calcium chloride in aqueous solution, and then determine what substance, if any, will precipitate. So these are how a lot of these problems are set up. They're going to be sort of spelled out for you in words. And so the first thing you have to do is get the formulas of the reactants correct. So we have sodium phosphate. Sodium is a +1 cation. Phosphate is a -3 anion. So the correct formula for sodium phosphate is going to be Na3PO4. And remember, in these reactions, we're telling you that they are in aqueous solution. The reactants will always be in aqueous solution, so you can write that AQ next to it. And then the other reactant is calcium chloride. Calcium is in the second column of the periodic table, so it's going to be +2. Chloride is -1, so it's going to be CaCl2. So if you need to refer back to the periodic table to predict the charges of those cations and anions, you can certainly do that, but I'll just write it out here with the correct formula. So you do need to be able to get the formulas of ionic compounds correctly to be able to balance these correctly. And then from there, we need to predict the products. So in many of these reactions, for both acid-base and precipitation reactions, we don't typically give you what the products are. You have to come up with those yourself. And the way that we do that for precipitation is we recognize that it's a precipitation reaction because it's 2 different ionic compounds reacting with each other, and then we just swap the cations and the anions from the 2 reactants. So the cation in the first is sodium Na+, and the anion in the second is chloride Cl-. So when sodium and chloride combine, they make NaCl as one of your products. And then the second product would be calcium, which is +2. This one, the formula is a little bit trickier to figure out. So the second cation here is calcium 2+, and the anion from the first reactant is phosphate PO4 3-. So this is one where if we want to get the correct formula for that, we take, again, charges and make them subscripts. So you would get Ca3 and then 2 PO4s, phosphates. All right, so that gives us the total charge being balanced. And so it's going to be Ca3PO4 2. All right, and then from there, the problem just asks us, well, we need the balanced equation, so we need coefficients potentially. And then we also have to identify the precipitate. So whatever order we do that in, we have to do both of those steps. So we can start with coefficients. So what we'll see is that, again, for these types of reactions, it's helpful to just balance it for each ion individually. So we see that here on the reactant side, we have 3 sodiums, Na3, so we need to have 3 on the product side, so that'll give us a coefficient of 3 there. And then if we look, we have 3 calciums as well on the, did I screw something up? No. What am I doing wrong here? now the chloride's not balanced. So what we're gonna have to do then is fix that to 6. See, sometimes you have to go back and forth a little bit. All right, so now our calcium is balanced, and then phosphate, we need 2 of them, so we're gonna put a 2 there. That keeps care of everything. All right, so I made a false move there. So sometimes when you add coefficients, you have to go back and change them afterwards. So if we try to balance sodium first, we end up not being able to balance chloride at the same time. But we got that by just doubling that coefficient. So now everything is balanced. We have 6 sodiums, 2 Na3, 6 Na. We have 2 phosphates there and then there, 3 calciums there and there, and a total of 6 chlorides. 3 times 2 is 6, 6 times 1. So those are the coefficients. And again, that's about as big as it'll get for a precipitation reaction. You typically have very small coefficients. Here, because of the -3 anion being involved, you ended up getting a coefficient of 6, which is pretty large for a precipitation reaction. Hard to imagine it being much bigger than that, but we have to make sure everything is balanced. And then usually the second most important step in writing one of these equations is identifying if there will be a precipitate. So for that, you need to think about the solubility rules we learned last time. All right, so looking at the first product here, NaCl, we should all appreciate that sodium chloride is soluble. It's what you would dissolve to make salt water. And again, that follows from the solubility rules. All salts that have sodium cations are soluble. There's really no exceptions to that you guys need to worry about. So that would be aqueous. It's going to remain in solution. And then if we go to the second product, calcium phosphate here, so there's a couple rules to think about, but phosphate is one of those anions that is almost always insoluble. So the only exceptions for phosphate being soluble would be if it is with, sodium or one of those other group 1A cations, lithium, potassium, cesium, rubidium, or if it's with ammonium. So anyway, phosphate is pretty much always going to be insoluble unless it's with one of those specific cations that makes it soluble, so that's going to be our precipitate there. All right, so we do form a solid that would precipitate out of solution, and that would be the correct way to balance this equation. Okay? So any questions on that one? All right, so the coefficients were a little bit trickier there, but we got there eventually. Now let's do an example of an acid-base reaction. So these have some similarities to precipitation reactions. The difference is that your cation from your acid is going to be H+ always, and then your anion from your base is always going to be OH-. So those two things are always involved in an acid-base reaction. H+ from the acid, OH- from the base. But then to balance the rest of it, of course, you need to know the correct formulas for both things. So here we have sulfuric acid. So remind ourselves of how we get formulas for acid. Sulfuric comes from sulfate. And so since it's SO4 2-, the acid would need 2 H+ to balance that charge. So it's going to be H2SO4. And then lithium hydroxide, the bases are typically just going to be hydroxide salts. So hydroxide, which is OH- with some cation. So lithium is Li+, hydroxide is OH-, so the formula for our base is just LiOH. Okay, so that's going to be the acid and the base, and those are what we're going to combine with each other in the acid-base reaction. And then for predicting the products for an acid-base reaction, it's always going to follow sort of the same format, where you have water is one of the products, because the H+ from the acid and the OH- from the base recombine to form water. So you're always going to get water as a product, and then the other product is just going to be the ionic compound that forms from the ions that are left over. So the cation from the base is lithium+, the anion from the acid is SO4 2-. So the ionic compound that forms from those two is going to be Li2SO4, lithium sulfate. All right, and all lithium salts are soluble, so that can be written as AQ. And then water usually is written as liquid water forms, but it goes into the solution, so it's essentially dissolved also. All right, so that's going to be the correct reactants and products, but now what it asks for is when the reaction is balanced with the smallest whole number of coefficients, how many moles of water are formed. So there's a pretty simple way of doing this for acid-base reactions, which is that you have to remember that to form water, you need 1 H+ and 1 OH-. So that's how water forms in these acid-base reactions, H+ plus OH- going to H2O. So it's always a 1-to-1 reaction between H+ and OH- to make water. And so what we see here is that our acid has 2 H pluses, is H2SO4. So that means we need 2 OH minuses to react, so we can put a coefficient of 2 there. And because we're reacting 2 of them, 2H plus, 2OH minus, we form 2 moles of water. All right, and then that should balance everything. We don't need a coefficient on the last product, even though the question wasn't even directly asking about that anyway. But to figure out how much water is formed, it's again 1 water for every H plus, every OH minus. They react 1 to 1. So if you have 2 H pluses, you also need 2 OH minuses, and you'll form 2 waters. So that's how we would approach that one. This is the full balanced equation, but really you didn't even need to go all the way as long as you recognize that you have 2 H pluses, meaning you'll need 2 OH minuses to react with that. Okay, so any questions on balancing those equations? I mean, that's mostly what we're going to do with acid, base, and precipitation reactions. Obviously for precipitation, you also need to know for solubility rules to identify your soluble and insoluble products. There's a little bit of an additional step there. But these are really the first 2 types of chemical reactions we've talked about where you're going to be expected to predict the products that form and then use that information to then eventually balance it with the correct coefficients. All right, so that's what we learned last time. That's just a quick review. So what we're going to step into today is a new type of aqueous reaction called a redox reaction. So redox is short for reduction oxidation. And so when you have a redox reaction, you're really having 2 things happening in the same reaction. They always go together. You can't have one without the other. So oxidation is when something loses electrons. So one of the reactants is going to lose electrons, and that's called an oxidation, or that means the reactant is being oxidized, is the way we say that. And then reduction is the opposite. One of the reactants will gain electrons. And so those 2 together will form what's called a redox reaction. And in any chemical reaction, you're not going to gain, or you're not going to create or destroy electrons. So that's why oxidation and reduction have to happen together. You can't have one without the other. If something loses electrons, something else has to gain those electrons that were lost. So they always go together as a redox reaction. And sort of stated pretty simply, a redox reaction is a reaction that involves transfer of electrons. So again, it involves one reactant losing electrons to form a product and another reactant gaining electrons to form another product. All right, so it always involves transfer of electrons between 2 things. And the previous 2 reactions that we talked about do not involve transferring electrons. They involve swapping cations and anions, but no electrons are exchanged between the reactants in an acid base or a precipitation reaction. But in redox reactions, they are. So there is a mnemonic device to help you remember which one is oxidation, which one's reduction. So Leo is the Latin root for lion, so you often see lions named Leo. And so if you write it out, so what does a lion say? A lion says gur. So Leo says gur. So if you lose electrons, that's oxidation. And if you gain electrons, reduction, exactly.
I remember that in biology, that last semester.
In where?
Introduction to biology.
Biology, yeah, you probably talk about redox in biology as well. It's very...
Biology covers things like a general field science, like chemistry, physics, all that.
Yep, but chemistry is the central science, so don't let anybody else tell you otherwise. It's the most important. But anyway, yes, you would definitely see redox reactions in biology. They're very important for cellular metabolism and for a lot of enzyme catalyzed reactions that occur inside of cells. Those are all redox reactions. We're going to talk about fairly simple ones in this class, and again, mostly how to balance them. So for redox reactions, just to give you a little bit of a preview of what's coming in this lecture, we're not going to ask you to predict the products of redox reactions. So for redox reactions, we'll always give you reactions and products. The main thing is to be able to balance them and then to be able to identify what's being oxidized, what's being reduced. That's what we have to learn today. Okay, so to do this, to be able to, first of all, identify whether something is a redox reaction or not, and then to balance it, and then to identify what's being oxidized, what's being reduced, we need to assign what are called oxidation numbers. So basically every element that appears in that chemical equation on the reaction side and the product side is going to be assigned an oxidation number. All right? And so for an oxidation number, there's a series of rules we have to learn. They're There's a lot of them, but they're not really as bad as solubility rules. First of all, there's more logic to it than solubility. And second of all, a lot of these we already know, even if we don't realize it. All right, so the first one is that there's only one specific situation when the oxidation number for an element will be 0, and that's when an oxidation number of an atom is 0, and that's only if it's in the form of a pure element. So if the atom is in the form of a pure neutral element, no charge, it's not a compound, it's an element, in that case the oxidation number is 0. So that would be if you have any metal by itself, sodium, iron, calcium, just by itself, no charge, no anion or anything that is paired with. If it's just the element, the oxidation number is 0, or any of the polyatomic elements, so H2, O2, N2, P4, S8, all those elements that appear as sort of polyatomic molecules. In that case, both atoms in those, or however many atoms those molecules have, would all have an oxidation number of 0. And that's the only time you see an oxidation number of 0. Every other time in any compound it's going to be non-zero. Okay, so that's how we do it. Now you might be wondering, what is how is oxidation number defined? I didn't really clearly define it, and we don't really need to worry about that for this class, but just in case you're curious, you guys remember when we covered formal charge in chapter 3 when we were talking about Lewis structures. And in formal charge, we assigned it as the charge an atom would have if we assume that the electrons are shared equally. Well, oxidation number assumes that all bonds are ionic. So basically, if you have two atoms bonded to each other, to assign the oxidation number, you assume that the more electronegative atom gets all the electrons that are shared. So it's a little bit different way of assigning sort of what are kind of like charges in a molecule, but it's useful because it allows you to identify whether something is being oxidized or reduced.
0, right?
Yeah, 0 is in the number.
Always stand for.
Oxidation number. So I use the abbreviation ON for oxidation number, just so I don't write it out a million times. And so you have you assume the electrons are given to the more electronegative atom, and it allows you to identify if something's being oxidized or reduced. Formal charge does not allow you to do that, so that's why we don't use it in this context. All right, now the other ones that are fairly simple that you'll see sometimes is a lot of redox equations are going to be written in ionic form, where you have individual ions participating, not necessarily in a compound. So if you have a single monoatomic ion, so Na+, Cl-, or any metal cation, any nonmetal anion, the oxidation number is just equal to the charge of that ion. All right? So all those group 1 cations, lithium plus, sodium plus, whatever, if they show up in a redox equation, their oxidation number is +1, the same as their charge. Or if you have an anion, O2 minus or Cl minus, the oxidation number is equal to the charge. So oxidation number can be positive, negative, or 0. Those are all possibilities. And then another important one, which maybe I should have listed first, but now it's going to make more sense when we start talking about compounds, is that for whatever species you're considering, whether it's a polyatomic ion, a molecule, or again, an individual ion, this works too, the sum of all the oxidation numbers in that compound or ion equals the overall charge. And that's kind of a shared rule with formal charges. Remember we said that the sum of the formal charges equals the total charge of the molecule, which would be 0, or the ion, which would be non-zero. The same is true for oxidation numbers. Even though they're defined differently and assigned differently, if you have something that has more than one atom bonded together in an ion or a molecule, all the oxidation numbers added together will equal the charge of whatever that ion or molecule is. So that means for neutral molecules, all the oxidation numbers add up to 0, just like all the formal charges do. And then for ions, they add up to whatever the charge of the ion is. Okay? Now the other ones that are fairly simple to do are, in most cases, metals are very straightforward, because metals, as we know, if they're going to be in a compound, it's going to be an ionic compound. That's the only type of compound we've talked about that has metals involved. And so if you have a metal in an ionic compound, they always have a positive charge. Remember, they always form the cations, and their oxidation number is just equal to whatever that charge is. All right, so we learned a long time ago, again back in probably chapter 3 or so, how to assign the charge of a metal in an ionic compound. We either use the periodic table if it's a main group metal in group 1 or group 2, or for transition metals it's variable, but we can figure out what it is based on the anions that it's paired with. And so once you know the charge of the metal in the ionic compound, that is also its oxidation number. So again, nothing more to it than that. So those 4 rules are pretty simple, because again, you're only going to see an oxidation number of 0 for neutral elements. Ions just have an oxidation number that's equal to their charge if it's just a monoatomic ion, single atom with a charge. And then for the metal as an ionic compounds, it's just equal to the charge as well. But for the rest, for the nonmetals that we're going to go through now, there's 4 additional rules that we need to know for nonmetals. And again, there's a few that are like a little bit tricky, but for the most parts, they're very straightforward to learn and very straightforward to use when we're assigning oxidation numbers. So if you have hydrogen in a compound or an ion, it only has 2 possible oxidation numbers. Now, of course, it's 0 if it's just hydrogen by itself, H2, but if it's in a compound with other elements, then it has 2 possibilities. It's almost always going to be +1, and that's going to be true anytime hydrogen is bonded to a nonmetal. Okay? So that's when it's bonded to a nonmetal. So if it's bonded to oxygen, carbon, nitrogen, whatever, it's going to have a +1 oxidation number. But it can also be -1, but it's not as common for this to be observed. But that's when it's bonded to a metal. So we haven't talked about hydrogen bonded to metals yet, but it can be involved in ionic compounds. We call those hydrides, where it's a metal plus hydrogen. Or if it's bonded to metalloids, that we might see a little bit more often. So that'd be like, especially boron, silicon being the 2 most common. So again, it's based on electronegativity. So if hydrogen is bonded to something that's more electronegative than it, which is most nonmetals, it'll be +1. If it's bonded to something that's less electronegative, like a metal or a metalloid, it would be -1. So those are the only 2 possibilities for hydrogen. It can never be anything else, and it's most commonly it's going to be +1, as I said. We don't see the -1 situation for hydrogen very often. All right, and then the next rule deals with fluorine, which is also a very easy one. So fluorine is the most electronegative element on the periodic table. We've talked about that a long time ago as well. And remember that in oxidation numbers, we're giving all the electrons to the more electronegative element. So that means fluorine, being the most electronegative, will always take all the electrons in whatever bond is involved with. So that means its oxidation number will always be -1 if it's in a compound. So again, by itself as an element, it would still be 0. So F2 would have an oxidation number of 0. But any compound that involves fluorine, HF, CF4, OF2, whatever it's bonded to, you're going to have an oxidation number of -1 for fluorine in any compound. And then oxygen is another one that's going to be almost always -2. So oxygen is the second most electronegative element. And so its oxidation number will almost always be -2 when you complete its octet and give it 8 electrons. But again, there's a couple of exceptions there. So if oxygen is bonded to itself, so in O2, it'll be 0 just like any other element, or if it's H2O2 where oxygen is bonded to itself, it'll be -1. There's a couple of exceptions where oxygen is bonded to itself where it's not -2, or again, if it's bonded to fluorine, because in that case, fluorine gets the -1 and then oxygen will typically have a positive oxidation number. But there's not very many compounds where oxygen and fluorine are bonded together, so again, not one you'll see a lot. But oxygen in almost every case is -2, so that's another one you'll want to quickly identify. And then finally, there's some, if you have chlorine, bromine, iodine, so the other halogens, except for fluorine, those are usually -1 unless they're the central atom. So if you have a polyatomic ion like perchlorate, where chlorine is the central atom, it won't be -1 in that case. And again, if it's bonded to something more electronegative than it, it won't typically be -1 either. So there's some variation there, but in the vast majority of compounds, all the rest of the halides are also -1 oxidation numbers. So those are the ones that you always see. The rest that I'm not showing, there's a lot of other elements that I haven't included yet, those ones typically have variable oxidation numbers. So for example, nitrogen, you don't see nitrogen anywhere here. Nitrogen can have a lot of possible oxidation numbers, and again, the way you figure it out is by following these other rules and then using rule number 3, the sum of the oxidation numbers equaling the total charge, to figure out what would it be for nitrogen in that case. So that's the one that changes its oxidation number a lot. So there's a lot of elements that have very variable oxidation numbers where you can't use simple rules, but you're usually going to use some of these rules in combination with rule 3 here to figure out what the oxidation numbers will be in those. So let's do a few examples then where we're just going to find out what the oxidation number is. All right, so let's determine the oxidation number of each element in sodium sulfide. So sodium sulfide is an ionic compound, metal and a nonmetal, it's binary. So this one ends up being a very simple one. So if we go to the periodic table, we should all be familiar by now with sodium being in group 1, which makes it a +1 cation in any ionic compound. And then sulfur is here in the same column as oxygen, so it will gain 2 electrons to get to the noble gas configuration. So sulfide will be -2. So for sodium sulfide, we have a +1 cation and a -2 anion. And so the formula for this compound would be Na2S, if we want to get the formula correct. But for oxidation numbers, remember that the oxidation numbers are just the charges of each ion. If it's an ionic a binary ionic compound in particular, we just have 2 ions and the oxidation numbers equal the charge in that case. So sodium will be +1 oxidation number. Each sodium is +1. There's 2 sodiums, each is +1, and then sulfur is -2. So that's going to be the oxidation numbers. And so for a binary ionic compound, it's very simple. It's just the charges of the ions, as we said. If you want to make sure that rule 3 checks out, which is that the sum of the oxidation numbers equals the overall charge, the overall charge of sodium sulfide is 0. We have 2 sodiums that are +1 each. And we have 1 sulfur that's -2, as we said, and so that adds up to 0. So that rule still will be followed in any type of compound, ionic or otherwise. The sum of the oxidation numbers for any neutral compound is 0. So using some combination of those insights, we can get that very simply. So for ionic compounds, especially the binary ionics, getting oxidation numbers doesn't require any additional insight besides just finding the charges of the ions. But then for here, we have one that's a little bit more complicated. So we want to know the oxidation number of each element in phosphoric acid. And so for phosphoric acid, we need to get the formula first. So phosphoric acid comes from the phosphate anion, which is PO4 3-. So the acid that would have PO4 3- requires 3 H pluses to balance. So it's going to be H3PO4. Okay, so what we need to do then is we need to find the oxidation numbers of each element, and for phosphorus in particular, we don't have a nice, clear, well-defined rule for that, so that one we're going to have to do sort of at the end after we get the other ones. So we have 3 elements in this compound, hydrogen, oxygen, and phosphorus, and the first 2, the oxidation numbers are very simple to find, because again, hydrogen, anytime that it's bonded to a non-metal is going to be +1. So in any acid or any covalent compound involving hydrogen, you're going to have +1 for hydrogen. And then oxygen, as we said, unless it's bonded to itself or unless it's in the elemental form or with fluorine, so there's a few exceptions for oxygen, but oxygen is almost always -2. So again, in almost every covalent compound, oxygen will be -2. Remember that the phosphate anion looks something like this if you draw the Lewis structure. So there's not going to be oxygen-oxygen bonds in any of these polyatomic anions. They're all just bonded to the central atom like that. So in all these cases, oxygen is bonded to a nonmetal. That's not fluorine, so it'll be -2. So we got hydrogen and oxygen fairly simply, because again, that's going to be what they almost always are in every compound. But for the rest, we have to follow that, as I listed it, as rule 3, which is that the sum of the oxidation numbers equals the overall charge to figure out what phosphorus is. So H3PO4 is neutral, so the sum of the oxidation numbers should equal 0. And so what we have in that compound is 3 hydrogens that each have a +1 oxidation number. Remember, the oxidation number applies to each individual atom in the compound, so that's hydrogen. We have 4 oxygen atoms that are each -2. And then we have 1 phosphorus with whatever its oxidation number is. So doing a little bit of algebra, what we can solve for is that the oxidation number for phosphorus, it's going to be +3 - 8 is -5. Move that over to the other side, we get a +5 for phosphorus to balance out all the charges. So the oxidation number for phosphorus is +5. All right, yes?
Why did you say it?
So because when we add up the oxidation numbers in a neutral compound, so H3PO4 has no net charge. When we add up the oxidation numbers, they have to equal 0, whatever the charge of that is.
What does they have to want, like
phosphorus. So that's our unknown oxidation number that we're sort of solving for using a little bit of algebra. So we don't know what phosphorus is right off the bat, but once we figure out what hydrogen and oxygen are, account for how many of each of them there are, then it's just a little bit of algebra to figure out what phosphorus has to be. So we just need to make sure that all of these add up to 0. 3 hydrogens, 1 phosphorus, 4 oxygens. That would come out to 0 if phosphorus is +5. One sort of helpful way to check yourself on oxidation numbers is that the maximum oxidation number for a main group element is going to be equal to the group number. So phosphorus is in group 5, so 5 is the highest it could be. So if you got 6, 7, or something higher than that, you know you did something wrong. So the group number tells you what the maximum oxidation number is, but it doesn't tell you what it is, it'll tell you what the maximum is. So that's a helpful way to check yourself, make sure you're on have a reasonable answer. But this is the maximum oxidation number for phosphorus +5, and that's what it comes out to here. All right. And then let's just do one where we have a net charge overall. So we're going to determine the oxidation number of each element in sulfate. So sulfate is SO4 2-. We have to remember the formula for it. And remember that in all of these polyatomic ions, these oxo anions, however many oxygen atoms you have, they're all individually bonded to the central atom. So in all of those cases, oxygen is going to be -2 because it's not bonded to fluorine, it's bonded, or oxygen is bonded to something less electronegative. So we'll have -2 for oxygen, but again, we have to do a little bit of algebra to figure out what the oxidation number is for sulfur, which we don't know, again, right off the bat. All right, so in this case, we're going to use the same trick as last time. The sum of the oxidation numbers equals the overall charge. The only difference is that this time the total charge is -2 is because it's an anion. It's not balanced with any charges from anything else. So our total charge is -2, and that's going to be equal to the sum of the oxidation numbers. So we have 4 oxygens that are -2 each, plus 1 sulfur, whatever that is. All right, so we're going to solve for the oxidation number of sulfur, which I used S as the sort of variable there. And so the oxidation number for sulfur is going to be equal to +6 to balance this out. So -8 plus 6 equals -2 the total charge. So we need a +6 on sulfur. All right, sulfur is in group 6. So again, as we said, the maximum oxidation number would be +6. But it won't always be +6, of course. It's just that's the maximum you can have. All right, so we get -2 and +6. Adding those together gives us -2, which is the overall charge. All right, so any questions on assigning oxidation numbers? All right, so we need to be able to do that, and we need to be able to do it quick. Oh, sorry, go ahead.
So, is there any situation where oxygen is not -2?
Yeah, so there are 2 or 3 situations where oxygen is not -2. So let's go through those quickly. All right, so if you have O2, again, any neutral element without a charge is going to be 0. All right, so it's just an element, there's no charge. If you have H2O2, so maybe not be obvious from the formula, but in H2O2, it's going to be sort of this connectivity where oxygen is bonded to itself. And so if you balance out the oxidation numbers, hydrogen has to be +1, and that means the total for oxygen is -2, but there's 2 of them, so in that case, oxygen will be -1, okay? So that's the case where oxygen is -1. Again, that needs to be true, because if each oxygen was -2, that would require each hydrogen to be +2, but hydrogen cannot be +2. So that is a couple ways of thinking about that. And then, again, a very rare example, but if you have OF2, which is an oxygen fluorine compound, fluorine is more electronegative, so it will always be -1. And if fluorine is -1, that makes oxygen +2 in this case. All right, so I don't think there's other exceptions than those ones there, but the most common ones are going to be these 2 here, where oxygen in its elemental form is 0, and if it's in hydrogen peroxide, it's -1. But look for oxygen first, because again, those exceptions are fairly rare, and it's usually going to be -2. All right, so the importance of oxidation numbers is that it allows us to, first of all, identify whether something is a redox reaction or not, and it also helps us balance it, as we'll see at the end of today. So that introduces some new terminology here, which is oxidizing agent and reducing agent. Now, these terminologies are a little bit confusing because the oxidizing agent is the reactant that does the oxidizing, which means it itself is getting reduced. So don't let that confuse you too much, but in a redox equation, we're going to have one reactant is going to be assigned as the oxidizing agent, one reactant is going to be assigned as the reducing agent, and the oxidizing agent is the reactant that gets reduced during the reaction. Again, an agent is someone or something that does something. So an oxidizing agent does the oxidizing, which means it itself is getting reduced. So it does the oxidizing, that's why we call it the oxidizing agent. And then how do we identify that using oxidation number? The oxidizing agent is going to have its oxidation number decreasing during the reaction. So that means whatever product has that element involved, if the oxidation number is changing, then the one that decreases is the oxidizing agent. So as an example, let's say we have a reaction where on one side of the area you have O2. This is not going to be a full reaction. There's going to be other reactants and products involved as well. But let's say on one side of the area you have O2, on the other side you have H2O. So oxygen goes from 0 oxidizing number in the reactant side to -2 on the product side. Its oxidation number is decreasing. That means oxygen would be the oxidizing agent in whatever this reaction is. I'm not writing it out in full. Okay, so it's the one that has its oxidation number decreasing during the reaction between the reactant and the product side. And we would call the oxidizing agent the entire ion or compound that includes that element that's being reduced. So it's the entire species, as we'll see later on. All right. And then the next one is that in a reducing agent is the opposite. So this is going to be the reactant that gets oxidized during an oxidation reaction, redox reaction. All right, and so again, we call it the reducing agent because it's the one that does the reducing. It's causing something else to be reduced, so it itself is being oxidized. And the oxidation number for the reducing agent increases during the reaction. All right, so as an example, let's say we had a reaction where we had NH3 on the reactant side. Again, there's going to be other reactants and products. You can't just have this by itself. But let's say we're looking at this species here. NH3 on the reactant side, N2 on the product side. The oxidation number for NH3 is -3 for nitrogen, is paired with 3 + 1 hydrogens. And then for N2 is an element, so it's going to be 0. So there'll be some coefficients and things and other reactants and other products that I'm not showing, but we would say that, okay, nitrogen has its oxidation number increasing. It's going from -3 to 0. So that means NH3, the entire molecule that nitrogen is part of, would be classified as the reducing agent. So again, in this case, this would be our reducing agent. And then up here in this partial reaction that I wrote, O2 would be your oxidizing agent. So that's how we identify what the oxidizing agent and reducing agent is based on what happens to its oxidation number during the redox equation. All right, so that'll become clearer as we do some examples. So let's go into some. So we have this reaction here. 2PCl3 plus O2 goes to 2POCl3. So there's two questions here. A, is this a redox reaction? And B, if so, what is the oxidizing agent? All right, so to answer both of these questions, we need to assign oxidation numbers for every element, every atom on the reactant and product side. So again, it seems unfamiliar now, so it might feel like this is going to take a long time, but you'll get good at these rules, you'll be able to do them quickly, and that's going to be necessary to be able to approach problems like this. So we don't have to worry about coefficients when we're assigning oxidation numbers, we just have to worry about the formula of each compound in the reaction. All right, so for PCl3, we said that chloride is almost always -1 unless it's bonded to something more or less negative like fluorine or something else, or it's a central atom. So here with chloride being the outer atom, chlorine is going to be -1. So if we have 3 -1 chlorines, to balance the charge we have to have a +3 oxidation number for phosphorus. So again, those group 5 elements in particular, nitrogen, phosphorus, they tend to have variable oxidation numbers. So here's going to be +3 to make sure that they're balanced. O2 is an element by itself. So it's going to be 0, no charge, no other elements in the compound, so it's going to be 0 for O2. Then if we go to the product POCl3, Again, phosphorus is variable, so we'll do that one last. Chlorine is still one of the outer atoms bonded to a less electronegative central atom, so it'll be -1. Oxygen is almost always -2 unless it's bonded to itself or fluorine, so that's going to be -2 for oxygen. So if we have 3 -1s and 1 -2, that's -5. So we need a +5 on phosphorus to be able to get the correct oxidation numbers balanced out. All right, so again, we typically do that one last because we're going to follow the rules for oxygen and chlorine to get their oxidation numbers and do that one by difference to make sure they all add up to 0. So those are the oxidation numbers for all of the elements, all the atoms on each side of the equation. So to identify if it is a redox reaction, we need to see, are there any oxidation numbers that are changing? All right, in any other type of reaction, acid-base or the ones we did last time, precipitation, you won't have any oxidation numbers changing. But for redox reactions, they do. And if we look here, we see that phosphorus is going from +3 to +5. So that oxidation number is changing. And if you have one oxidation number that's getting bigger, you need to also have one that's getting smaller. Remember, they always happen together, oxidation and reduction. And oxygen we see is going from 0 to -2. Okay? So we have a pair of changing oxidation numbers, which you always will have in a redox reaction. And so the answer to this would be yes, this is a redox reaction. Okay? Anytime you see changing oxidation numbers from the reaction side to the product side, phosphorus going +3 to +5, oxygen going from 0 to -2, that identifies it as a redox reaction. So that part is done. And then from here, we have to identify what is the oxidizing agent. So the oxidizing agent is the one that gets reduced. Again, the terminology can be a little bit confusing when you're first learning it. The oxidizing agent gets reduced, and what it means to get reduced is that your oxidation number decreases during the reaction, from reaction to product side. So the one that's decreasing is oxygen. Oxygen is going from 0 to -2, and so that means O2 is the oxidizing agent. The whole thing that has the oxidation number that's reducing is the oxidizing agent. So that's going to be O2. All right, its oxidation number is getting smaller, going from 0 to -2. That identifies it as the oxidizing agent, the one that is getting reduced. Okay? So reducing, another way to remember is that reducing means the oxidation number is getting smaller. If it's getting reduced, then the oxidation number is getting smaller, but that makes it the oxidizing agent, so don't be confused by that. All right, so any questions on that, how we identify redox reactions, how we identify oxidizing and reducing agents? Okay, so let's do one more just like that. Another reaction this time, and we want to identify if it's a redox reaction. Now, when we're doing problems like this, if we're asking you to classify the reaction type, the first thing you can look at is, does it fit clearly with one of the other categories of reaction we've already learned? So is it an acid-base reaction? Obviously. Does it have, an acid and a base making a water an ionic compound? Or is it a precipitation reaction? 2 ionic compounds reacting to make 2 other ionic compounds. If it clearly fits one of those other 2 categories, then you don't necessarily have to go through all the trouble of finding out all the oxidation numbers. But here, we can't easily tell, right? It's not one of those obvious cases where it's not an acid and a base making water and an ionic compound. It's not 2 ionic compounds reacting to make 2 other ionic compounds. So we can't easily tell if it's an acid-base reaction or a precipitation reaction just by looking at it, but that also doesn't mean it's a redox reaction. We still have to then go through and assign oxidation numbers to figure out if it actually is a redox reaction or not. So we're going to have to do the same approach that we did the last time, which is assigning all of the oxidation numbers. So POCl3 was the product in the last reaction. So if you recall, the oxidation numbers we got for that were -1 for chlorine, -2 for oxygen, following those rules, and that leaves +5 for phosphorus. Here we have water. We're going to see water a lot in redox reactions, so we should be able to quickly assign this as -2 for oxygen, +1 for each hydrogen. Remember, hydrogen is +1 if it's bonded to a nonmetal. Oxygen is -2 unless it's bonded to itself or fluorine. And then for the product side, H3PO4, I don't think we did that one yet. Or maybe we did that one earlier, so we did that one also earlier, but let's remind ourselves of that. Oxygen -2 in a covalent compound, hydrogen +1 in a covalent compound, so we have -8, +3 is -5. That means we need a +5 on phosphorus to balance those oxidation numbers and make them equal to 0 for the overall charge. And then the other product is HCl. Again, hydrogen +1 in any covalent compound for the most part, and chlorine -1 unless it's the central atom. So here, +1, -1, those cancel out to give you 0. So if we look at the oxidation numbers in this reaction, we have 4 different elements involved: phosphorus, oxygen, chlorine, and hydrogen. We see that phosphorus on the reactant side is +5, and on the product side is +5, so that's not changing. Oxygen is -2 in 2 places on the reactant side, both here in POCl3 and here in H2O, it's -2. And on the product side, oxygen only appears once, and it's still -2. For chlorine, it's -1 here on the reactant side in POCl3, and on the product side, it's also -1. And then finally, hydrogen, we saw that it was always in covalent compounds, so it's going to be +1 in water. And then on the product side, we have hydrogen appearing twice, but it's +1 in both cases. +1 for H3PO4, +1 for HCl, hydrogen stays the same. So all of the oxidation numbers are staying the same between the reactants and the product side, which means that this is not a redox reaction. And it turns out that this actually is an acid-base reaction. It's not one that we can obviously identify as such using the general chemistry definition of acid-base reactions that we learned, but nonetheless it is an acid-base reaction. So we wouldn't expect you to know that it's an acid-base reaction, but we would expect you to know that it's not a redox reaction for sure, because it doesn't have any oxidation numbers that are changing. Okay, so this one is not an oxidation reaction, a redox reaction, so that means we don't even have to answer part B, because there is no oxidizing agent unless it is a redox reaction, okay? So any questions on that one? Same approach, but this time we found that there were no changing oxidation numbers, so it's not, in fact, a redox reaction. All right, so the last thing we need to cover then is how to balance redox reactions. So this is going to be a big thing, and then to give you a little bit of a history on this, so a lot of the homework and test questions you guys have, and we've sort of refined them over the years. I'm not saying we just keep the same ones all the time, but a lot of them were written over the years by a retired professor named Professor Gene Angel. I don't know if any of you have heard of him. And he loves balancing redox reactions. It's like his favorite thing in the world. So what that means is you will almost definitely on the next exam see 2 problems where you have to balance redox reactions. I haven't looked that far ahead myself, but expect this to be a significant part of both the midterm exam that's coming up and the final exam at the end. Because again, the person that sort of organized a lot of our test banks and all that stuff that we still kind of follow for the most part, he loved balancing redox reactions, so it's going to be a big thing. All right, so let's go through then and talk about the steps then for doing this. So in a typical redox equation, what we would do is we give you all the reactants and products, and then you have to go and provide the coefficients for us. Now, you don't want to do these by inspection, and there's a few reasons for that. So one is that in a lot of cases in redox equations, you have charged reactants and products. And in order for it to be balanced, you not only have to make sure that the atoms are balanced, but also that the charges are balanced. So whatever net charge you have on the left side of the arrow, you have to have the same net charge on the right. And it's hard to do that just by guessing and checking. So you do want to follow this approach for balancing redox reactions, which is much more systematic and allows you to get it much more effectively than just trying to do a guess and check approach. So we're going to use what's called the oxidation number approach. So as the name suggests, the first thing we need to do is we need to assign the oxidation numbers for all the reactants and products. So I don't want to say that it's never possible to balance a redox equation by, by inspection, by just using coefficients and kind of just guessing and checking as you go along. But it's not the best way to do it in most cases, and it will, in many cases, lead you down a dead end or lead you to an answer that you think might be correct, but actually has something a little bit off about the coefficients. So you want to follow this approach in every case. So we're going to assign the oxidation numbers for each atom on the reactants and product side. So in this one here, it's written as an ionic equation, so we don't have, we have a lot of charges involved. So for an ion by itself, the oxidation number is just equal to the charge, -1 for Cl-. Permanganate is a polyatomic, so in this case we have to go through and figure out the oxidation numbers. Oxygen is going to be -2, except for those rare cases we talked about. And so if we have 4 -2 oxygens, that's -8. The overall needs to be -1 for the charge to be balanced out. So -8 plus 7 equals -1. All right, so again, we're doing that by difference or by, simple algebra. 4 minus 2s is minus 8, plus 7, add those together, you get minus 1, which is the overall charge of the ion. So for polyatomic ions, that's the approach you have to take. And then we have H plus by itself, so the oxidation number is just the charge plus 1. So for ions by themselves, the oxidation numbers are very simple. On the product side, we have another polyatomic, so a little bit simpler one, but still one that we're going to have to go through and find in a little bit longer approach. Oxygen bonded to anything besides itself, or fluorine, is minus 2. So we have minus 2 for oxygen. The overall charge is minus 1, and so that means for those to add up, you need a plus 1 for chlorine. All right, so we said chlorine will be minus 1 unless it's the central atom or bonded to something more electronegative. Here, chlorine is bonded to oxygen, so it's not going to be minus 1 because oxygen is more electronegative. So minus 2 plus 1 is minus 1. That adds up. Manganese is by itself as a plus 3 cation, so it's going to be just plus 3 for that product. And then water, our old friend that we'll see in a lot of redox reactions, plus 1 for hydrogen, minus 2 for oxygen. That one we should be able to do without thinking after practicing this a few times. Okay, so that's all the oxidation numbers. You have to go through and do that to be able to, figure out. That's really the first step that's involved. There's really no shortcut around that in most cases. So the next step is we're going to determine the number of electrons lost and gained for each species that changes its oxidation number. All right, so in any redox reaction, something's going to lose electrons, something's going to gain electrons. We have to figure out how many electrons are being lost and gained in each case. Maybe I'll just change species to reactants. Remember, we're going to do this we're going to be able to identify one as oxidizing agent, one as reducing agent if we want to. So let's just focus on the ones that are changing. We wrote out all the oxidation numbers, but now for the rest of the time for the balancing, what we really need to just focus on are the ones that are changing oxidation numbers. So we see that chlorine is going from minus 1 on the reactant side to plus 1 on the product side. So we're going to need to look at that one. The ones that are changing now are chlorine, which is minus 1 to plus 1. And the other one that's changing, which I'll write in a different color for now, is manganese. Mn goes from plus 7 on the reactant side to plus 3 on the product side. All right, so we have, again, 2 sets of changing oxidation numbers. You always have that in a redox reaction. So we have to then figure out how many electrons are being lost and gained in each case. And to do that, it's going to be determined by the difference, how much the oxidation number is changing. So for chloride, we're going from minus 1 to plus 1. So the difference between minus 1 and plus 1 is how many electrons? 2. It's just subtraction, so nothing difficult there. So that one is, if we want to keep track closely, it's losing 2 electrons. Now, we don't necessarily need to keep track of whether it's losing or gaining electrons, because again, one thing will lose electrons, one thing will gain electrons. For balancing, it's not so important to know which one is which. If you're asking again for oxidizing agent, reducing agent, you might need to look at that. But this one is technically losing 2 electrons, but the important thing is that it's a 2-electron process. The change in oxidation number is by 2, so that means there's 2 electrons. And then if we look at the other one, manganese, it's going from plus 7 to plus 3, so how many electrons would that be? 4, it's a difference of 4. In this case, it'd be gaining 4 electrons because the oxidation number is getting smaller by 4 electrons. But as I said, it's not so important to recognize which one is gaining, which one's losing, but you do need to know how many there are. 2 electrons for this one, difference of 2. 4 electrons for the other one, difference of 4. So then from there, what we have to do is we're going to start adding some coefficients to make sure that the number of electrons that are lost are equal to the number of electrons that are gained. So that's the first set of coefficients we're going to add. So we always start with coefficients on the reactants and products that are changing their oxidation numbers as we go across the arrow. So we said, as we said that Cl minus to ClO minus was a 2-electron process. And we said that MnO4 minus to Mn3 plus was a 4-electron process. And these two numbers need to end up being equal to each other, because as we said, in a redox reaction, you're not creating or destroying electrons. However many electrons one thing loses have to be gained by the other thing. So it's a 4 and a 2 here, so they're not equal right now. So the way that we deal with that is we have to double the coefficients for both of those. Okay, so we're going to put a 2 there and a 2 there. We double the coefficients on both things that are involved in that 2-electron process. So now it's a total of 4 electrons. It's 2 electrons for each chlorine, but it's now happening twice because of the coefficients of 2. So a total of 4 electrons there. And then for this one, we don't need coefficients. So we're going to put, just remind ourselves, we're going to put coefficients of 1 there. All right, because we only need 1 of those. That'll be 4 electrons total. This one happens twice to also give us 4 electrons total. So the number of electrons need to be balanced, and we do that by adding appropriate coefficients to each of the reactants and products that are involved in the electron transfer processes, the ones that are changing their oxidation numbers. So at this point, we don't want to change the coefficients on any of these reactants and products. So the ones that we've set so far, 2 for Cl-, 1 for permanganate, 2 for hypochlorite, 1 for manganese 3+, those coefficients, we don't want to adjust them anymore because that will throw off the balance of the number of electrons. We have to leave those the same. So the rest of this is what we just balance by inspection. So the last step for any reactants and products that don't yet have coefficients set, we're going to just balance them by inspection, which again, just make sure that the number of atoms is balanced on the left and right side. And so what we'll see is that if we set that to 2, that to 1, that to 2, that to 1, we have to just balance H plus and water. That's commonly what you'll have to do. You have to balance H plus and water at the end. So to look at how we balance this, what we see is that on the reactant side, we have 4 oxygens from MnO4-. On the product side right now, we just have 2 from ClO-. So that means we also need to have 2 more from water to make sure that oxygen is balanced. So by putting a 2 there, we're going to have 2 times 1 is 2 plus 2, 4 oxygens on the right and 4 oxygens on the left. So we usually balance water first to make sure that the number of oxygen atoms on both sides is the same. And then once we've done that, we can add in the correct number of hydrogens from H+. So on the right side, we now have 4 hydrogens from water, 2 H2O. So that means we need to have 4 H pluses on the left to balance hydrogen. So it's not always going to be like that, but that's very commonly what you'll see at the end of a redox reaction. You're going to add water to one side to make sure that you have the correct number of oxygen atoms on both sides, and then you'll add H plus to the other side to make sure there's the correct number of hydrogen atoms after you've added the water. So that's the kind of series of steps that we'll do there to get the last 2 coefficients. So the coefficients for this are 2, 1, 4, 2, 1, 2. So those ones are not terribly difficult or terribly huge, but we use that approach to get them. And as we'll see, in some cases, we're going to have coefficients that are much bigger than that involved, and then using this oxidation number approach, it won't be too difficult to get those. All right, so questions on that process before we practice it a couple more times before we close out today. All right, so we're just going to go through a few examples now just to see some of the different variations you can have. So this is, again, a standard redox reaction. This time it's dichromate plus iodide and H+, making chromium-3, I2, and water. All right, so we have to assign the oxidation numbers first. So dichromate is a tough one. There's a lot of atoms involved, and there's a charge as well. But again, oxygen bonded to a metal is going to be -2. We have 7 -2s, that's -14. The overall needs to be -2 because it's a 2- anion, so we need to have +12 from chromium, right? So +12 -14 is -2. We can write that out a little bit more differently. So again, the overall charge is -2. We have 7 -2s from oxygen. And then we have, how much do we need from chromium? We need a total of +12 to balance that out, but there's 2 chromiums, so each is going to be +6. All right? Again, the oxidation number applies to each atom in the formula. So 2 +6s, each chromium is +6, that's +12. 7 -2 is -14, 12 -14 is -2, which is the overall charge. So that one was particularly difficult to get the oxidation number, but thankfully the rest of this in this problem are very easy. So I-, ion by itself, oxidation number is equal to the charge. H+, ion by itself, oxidation number equals the charge. Chromium 3+, ion by itself, oxidation number equals the charge. And then I2 is an element with no charge. It's not bonded to anything else, and there's no charge. So that's the one case where we'll have a 0 oxidation number, and then our old friend water, +1 and -2. Okay? So the rest of the oxidation numbers were very simple. The first one you had to do a little bit of work to get. Now, this is the type of problem where when we start in this situation here, sometimes there's a couple different ways of handling it, but what you'll notice right away is that on the reactant side, we have dichromate, Cr2O7 2-, but on the product side, it's just chromium by itself. So what that means is no matter what coefficients we have for Cr2O7 and Cr3+, you need to have double the coefficient over here to keep chromium balanced. So the atoms still need to be balanced. So what I like to do, not everybody does it this way, but what I like to do is I like to put a 2 there right away. Now that's not necessarily going to be the final coefficient, but it just reminds myself that whatever coefficient I have here needs to be 2 times whatever coefficient I put here to keep the chromium balanced. So you may or may not like that approach, but that's how I'll typically do it. So then from there we can go forward and start figuring out which oxidation numbers are changing and how many electrons are involved. So we'll see that chromium goes from +6 to +3. So that is a difference of 3 electrons for each chromium, but again, there's 2 chromiums involved, dichromate, Cr2, and then O7 2-, and forming 2 chromium 3+. So it's 3 electrons each, chromium, +6 to +3 is a difference of 3, but that's happening to 2 different chromium atoms. Each one of those is going from +6 to +3. So in reality, as it's written now, that's a 6 electron change, because it's 2 + 6 going to 2 + 3s, 3 electrons for each, total of 6. And then for I-, it's the same story. We actually have, we didn't put that in yet, but iodine appears here on the reactant side by itself. Here on the product side is I2. So again, to remind myself that we need a double coefficient, I'll put a 2 there to start. So that's going to be 2, and that's going to be whatever that coefficient is going to be, half of that. So that electron change, what we have is each one is going from -1 to 0, so that's 1 electron per each iodine. But there's 2 of them. 2 I- is going to I2. Each one of those is changing by 2 electrons. So it's a total of 2 electrons as I've written it now. So again, how you count electrons in this can be, there's a couple different ways of doing it, but this is how I like to do it to make sure that I remember to keep the coefficients in the right relative amount and also to count the electrons correctly. All right, so we got a 6 electron and a 2 electron. So what that means is right now the electrons are not balanced. This is 6, this is 2. The way that we make them balanced is we have to triple the iodide coefficients and the I2 coefficients. So what that leads to then is we're going to set the coefficients here as 1 and 2 for Cr2O7 2-. But then for iodide we have to triple the coefficient. So it started out as 2, we're going to triple that to 6. H+ we haven't added yet, so we'll leave that without a coefficient. And then the product side, again, we're going to set that to a coefficient of 1, that's a coefficient of 2. We don't need to change those to balance electrons. But then the coefficient on I2 needs to be tripled from what it started with to balance the electrons, so that's going to become 3. And then we have water to add on at the end. All right, so that's going to be the coefficients that are now set for the first 2 reactants and the first 2 products, the ones that are being oxidized and reduced. And we did that to make sure that it was a total of 6 electrons for both the oxidation and the reduction. So chromium is losing 3 electrons each, 2 of them, so it's a total of 6. And now what we have is 6 I- going to 6 I-, so that's a total of 6 electrons also. So sometimes counting electrons is a little bit trickier if you have coefficients like this involved, but we get it and we get it balanced out. And now all that's left is to balance water and H+ by inspection. So right now on the reactant side we have 7 oxygens, so we need to have 7 waters to balance oxygen. By adding 7 waters, that introduces 14 hydrogens on the right side. To make sure we have 14 on the left, we're going to put a 14 in front of H+. So again, water and H+ typically getting balanced last in that order to make sure that both oxygen and hydrogen will end up being balanced. All right, so any questions on that one? That one was a little bit more involved, but so that was a slightly more difficult one, but it required us to again account for the fact that we have different numbers of atoms in the reactants and products for the species that are being oxidized and reduced. So we have to account for that when we're counting the electrons up and make sure we're getting the right number. All right, anything else on that one? All right, I think we're just going to do two more. All right, so we have this one here, KiO4, which is called potassium periodate, plus NH3 going to Ki plus N2 plus H2O. Now, just like we saw before for other types of chemical equations, a lot of times what we'll do in Blackboard is we'll say balance the equation with the smallest whole numbers and then determine the sum of the coefficients. That's what we're doing here. Again, there's no value of having the sum of the coefficients. It's just a way for us to ask you in Blackboard if you got the answer right or not, because you can't write out the whole equation, obviously. So we're going to do that here. This one I think is a little bit more straightforward than the last one, but let's go through it. Now we still have, though, a little bit of the same issue as we did in the previous one with one of the reactants, which is that for nitrogen we have NH3 on the reactant side, which has one nitrogen. On the product side we have N2, which has two nitrogens. So again, whatever the coefficient is on NH3 has to be 2 times whatever the coefficient is on N2 to make sure that we have the correct number of nitrogen atoms on both sides. How you choose to handle that is up to you, but I'll start by putting a coefficient of 2 there, just to remind myself that whatever this coefficient is needs to be twice whatever the coefficient is there. But we have to go through then the rest of this to get the correct coefficient set. Okay, so for KiO4, this is an ionic compound, so potassium will be in this +1 charge or +1 oxidation state. Oxygen will be -2 in any, compound that is not bonded to itself. And then we have to figure out iodine by difference. So we have 4 -2s, that's -8. +1 is -7. To balance that out, we need a +7 on iodine. So iodine is in group 7, +7 is the largest oxidation number it can have. 4 -2s for oxygen is -8. A +1 for potassium, that's -7. +7 all adds up to 0 for the overall charge-neutral compound KiO4. NH3 is a little bit simpler, so what we have for NH3 is in a covalent compound, hydrogen will be +1. And so if we have 3 +1s, that's +3. We need a -3 on nitrogen to balance that out. So +3 -3 cancels out. Potassium iodide is a little bit simpler. It's a binary ionic compound. So potassium will still be +1 if it's an ionic compound in any case, and then that makes iodine -1. So for binary ionics, it's just the charge of the ions, +1 and -1. N2 is an element by itself with no charge, so it'll be 0. So again, elements are the ones that'll have 0 oxidation numbers. And then finally, water are the one that we see almost all the time, +1 and -2. Now what we've seen in a few of these now, and I want to just point it out to you, is one way that you can quickly identify a redox reaction. It's not going to be applicable to all redox reactions, but any reaction that involves a neutral element. So here N2, or a previous one we had O2, or if you just have a metal, sodium, iron, whatever, if that's one of your reactants or products, that has to be a redox reaction. Because remember, the elemental form is the only time the oxidation number will be 0. So if that's changing to something else, then it has to be something that's not 0 on the other side of the arrow, and so that means that would be a redox reaction because something is changing its oxidation number. So if we give you a problem where we give you, like a list of a few reactions and we say, which of these are redox reactions? Well, if you see any of them that have elements as a reactant or a product, again, element by itself with no charge, that has to be a redox reaction. So that doesn't really come into play for balancing it, but again, for identifying redox reactions, that's a helpful shortcut for some of them. It won't apply in all cases. But this one, we have to find the ones that are changing. So iodine is going from +7 to -1. So what's the difference between +7 and -1? Someone say it. I'm not going to say it. I heard a 6 and I heard an 8. I like 8 a little bit better. So because it's +7 to -1. So that's a difference of 8 if you look on the number line or just do subtraction. So 7 minus -1 is 8. And then for nitrogen, we have that one also changing. It's going from -3 to 0. And again, we have to make sure we count electrons correctly because each nitrogen is changing by 3. It's going from -3 to 0. So that's 3 electrons each. But that's happening for 2 nitrogen atoms. So we're forming N2, where each of the atoms is 0. And we're starting with 2 NH3s to make sure that the nitrogen is balanced. So it's going to be -3 for each one. Or I guess, sorry, that's +3 electrons, but sorry, that is, no, it's -3 electrons for each one, but happening twice. So that's a total of 6 electrons. So right now the electrons are not balanced. We have 6 electrons for this. This is the oxidation part, and then for the reduction part we have 8. So we have to make sure that those number of electrons are the same. So how do we make those the same, 6 and 8? What factors can we multiply by to get them the same? So this requires a little bit of math and a little bit of thought. So if you're using mathematical terminology, you're looking for, what is it, the least common multiple of 6 and 8, okay? So what would that be? Let's see, it's not 12, not 18. 24, good. So we need to have both these equal to 24. That's the smallest number of electrons we can get to make those two balance each other. All right, so we're going to multiply that by 3 to make it 24. We're going to multiply that by 4 to make it 24. There's no smaller common multiple that we can think of for those two numbers. All right, if you try to do it, if you use 6 as your starting point, 6 can be doubled to 12, but that's not a whole number multiple for 8. It can be tripled to 18, but that's not a whole number multiple for 8. But if you quadruple it to 24, that is also a whole number multiple of 8. So this time it's a lot of electrons to make sure it's balanced, but that's what we're going to end up with here. So what that means is we need to triple the coefficients on KiO4 and Ki. So we're going to get a 3 there, and a 3 on Ki. And then for NH3, we have to quadruple the coefficient. We have to multiply that by 4 to make it 24 electrons. So that one goes from 2 to 8. And we're going to do, and there's no other reactants, so that's it. And then on the product side, we have to go, this one was quadrupled as well. So instead of 1 N2, it's going to be 4 N2s. Then we have to do water last by inspection. All right. So to figure out how much water we need, so that's our reactants and products, and the only thing that's missing is the coefficient for water. We just, again, have to look at how much oxygen we have. So here we have 3 times 4 is 12 oxygens on the left side, so we have to make sure we have 12 on the right. That gets a coefficient of 12. Now we have to also check that hydrogen is balanced, because we didn't do that one separately in this case, but here we have 12 times 2 is 24 hydrogens. Here we have 8 times 3 is also 24. So whether you chose to balance hydrogen or oxygen first, you just put a coefficient of 12 in front of water, and that's all you need to balance the rest. Again, once we set these coefficients here for the ones that are being oxidized and reduced, we don't want to change them after the fact. So we'll keep those as they are, and we'll just adjust the coefficient on water to make sure that everything else is completely balanced. So those are the coefficients, pretty large, probably not likely that you would come up with that by inspection. It would take a long time to try to guess and check yourself on that one. So using the oxidation number approach, though, we get those. They can't be reduced any further. And so now we just look for the sum to answer this question as in the correct format. So the sum is going to be 3 plus 8 is 11, plus 3 is 14, plus 4 is 18, plus 12 is 30. So the sum of the coefficients that we would report is 30 for this one. It's not likely you would guess that number correctly, so that's often why we ask questions in this way.
What do we use, like, units, 30 and 20?
What do we use for what? I'm sorry?
Like 30, like the units for 30, like 30 and 20.
Well, 30 is just the sum of the coefficients, so you don't really need a unit. And if we ask you for a numerical answer in Blackboard, we won't ask you to put units in anyway, so you would just type the number 30 for that. I mean, it can be thought of as, I guess 30 moles would be one way to think of the units, but you don't need to put that in. It's just the sum of the coefficients, which are just numbers, so you just add those up. Okay, anything else on that one? All right, last one here before we adjourn for spring break, which this one has one more little, I guess, I don't want to say trick, but one other little additional feature that we have to account for in some of these redox reactions. So we'll start out this one normally. We're just going to assign oxidation numbers as normal. So we have zinc, which is an element by itself. That's going to be 0. And then what we have is HNO3. So we're going to have -2 and +1 for oxygen and hydrogen. That's -6. That's +1 is -5. So we need a +5 on nitrogen to balance that out. So we have +5 there. And then on the product side, what we have is zinc nitrate. So we can think about this as an ionic compound. So it's 2 NO3 minuses. So that means the charge on the metal is +2. And zinc is always +2 in ionic compounds. It's not the most obvious one from the periodic table, but that would always be the case. And then for NO3 minus, it's still just nitrate. So it's going to, for each one, we're going to have -2 for oxygen, and +5 for nitrogen to make it NO3 minus. All right, again, you can do that either all intact. We have +2 for zinc, and then we have 6 oxygens and 2 nitrogens. But again, we can just think of it as an ion NO3 minus, where we have 3 -2s for oxygen, a +5 for nitrogen. That will equal up to the -1 charge of the anion. So that's going to be +5 and -2. And then for NO, simple diatomic, a little bit easier, -2 for oxygen. That leaves +2 for nitrogen to balance those out to equal 0. And then water, which we almost always see, is going to be +1 and -2. So those are the oxidation numbers. And the problem that we have in this case, so we can identify the ones that are changing. We have zinc going from 0 to +2. That's pretty easily a 2-electron process. And then we have nitrogen going from +5 to +2. That's pretty easily a 3-electron process. But the other issue that we have in this problem is that we have some nitrogen that's staying at +5. Because nitrogen only appears once on the reactant side in HNO3, but it appears twice on the product side. In some of the product, it's going to be +5, and the other product is going to be +2. So the way that I like to handle this then is balance HNO3 in 2 parts. So some of the HNO3 is going to change its oxidation number and become NO, and we're going to balance that by making sure the number of electrons is the same for both processes. But some of the HNO3 is going to not change its oxidation number, it's just going to go from HNO3 to nitrate, NO3 minus, and those will balance by inspection at the end to make sure it's totally balanced. So I like to break it up into 2 pieces. It looks a little weird to do it this way, but it helps, I think, make sure that you're keeping the correct number of electrons and everything like that. So what we're going to do is when I balance this, I'm going to write HNO3 twice. And so then what I'm going to do is part of this I'm going to balance at first using the number of electrons. The other part of it I'm going to balance at the end to make sure I have the correct number of nitrogen atoms total, because there's going to be some of that that's not changing its oxidation number. So let's do we always have to start by balancing number of electrons. That's always going to be the first step. So we have 2 electrons and 3 electrons. So what's the least common multiple of 2 and 3? 6. So we're going to triple that, and we're going to double that. So we tripled the coefficients on zinc and zinc nitrates. They become 3. And then we double the coefficients on the first HNO3 and NO, so they become 2. So those coefficients that we added, we're going to leave as is, 3, 2, 3, 2, but now we have to balance the rest by inspection. So we're going to add some additional HNO3 to make sure we have the right number of nitrogen, and then we're going to add water to make sure that oxygen and hydrogen are balanced. So I think the correct order to do this in is let's balance nitrogen first. So right now on the product side, because all the coefficients are set for the 2 products that have nitrogen in them, we have 2 times 3 is 6, plus 2 is 8 nitrogens. So 2 of them come from here. That means we need 6 more HNO3s to balance out the nitrogen on the right side. Or another way to think of that is we have 6 nitrate counterions here with zinc nitrate, and those 6 nitrates came from our 6 HNO3s on the reactant side, so we have to add 6 more there. And then to make sure water is balanced, this is the one that's going to be a little bit more of a hassle, but for water what we have is, on the reactant side right now, we have 2 times 3 is 6 plus 18, so we have 24 oxygens on the left side. On the right side, what we have so far is that's going to be 6 times 3 is 18, plus 2 is 20. So 20, 2 oxygens. It looks like a 0, but it's an O. So we have 20 oxygens right now, so that means we need 4 more from water, so we get a coefficient of 4 there. So you have to make sure the number of oxygen atoms is the same on both sides. So it's 24 here from the nitric acid that we have on the reactant side. We have 18 there, 2 more there is 20. We need 4 more from water. So that gets everything balanced out, and then we're just going to simplify to this. So when you write the reaction out in its final form, you obviously don't write HNO3 twice, we just combine them. So it's going to be 3 zinc plus 8 HNO3, 2 plus 6, the combined coefficient is 8, goes to 3 zinc nitrates, 2 NOs, and 4 waters. All right, so the only difference here was we had to balance HNO3 in some part to make sure the number of electrons was correct. Then we had to add additional HNO3 to make sure that we have total atom balance in the product side as well. So the way I like to approach that, as I did here, is in 2 parts. All right, any last questions on that? All right, okay, I think we're all ready for spring break, so have a good week off. I will be in my office most of this afternoon until 3 o'clock, so if you need to come see me, please do. If not, I will see you guys after the break.